Okay, so now we're in business. All right. So we're going to continue our discussion of chapter 12. And now we'll be looking at the topic of electronegativity. So before, we were talking about bonding, covalent bonding in particular. And basically, just to recap a bit, covalent bonding involves the sharing of electrons. And in most cases that we discussed, the atoms will try to end up with a full outer shell or octet in most cases of electrons so that each atom will be stable. And we talked about the Lewis symbols for simple molecules like the ones that you're looking at on the screen. And we can use these representations, or we can use a line to represent a shared pair of electrons. And we can also use a line to represent these electrons which are not shared. So each dash represents a pair of electrons, all right? I think that's where we stopped the last time. So now that we have talked about covalent bonding, we can talk about the concept of electronegativity. And electronegativity is basically the relative attraction that an atom has for electrons it shares with another atom in a covalent bond. So if you have two atoms connected to each other by a covalent bond, then the electronegativity of the atoms is the relative attraction that a particular atom will have for the shared electrons. So if you consider a situation where two atoms are identical, then obviously they will have equal attraction for the electrons that are shared. So we're talking about examples like the ones that we saw before. For example, let me get my pen. So for example, the hydrogen molecule, where you have, okay, oh shoot, my thing is not plugged in. Sorry about that, folks. Let me take care of this now. Okay, so in the case of the hydrogen molecule, where you have two identical atoms connected to each other by a covalent bond, these electrons here, the pair of electrons here, would be equally shared between the two atoms because the two atoms are identical. So we call this type of bonding a nonpolar covalent bond, all right? And that is true not only for hydrogen, true for pretty much all the diatomics that we were exposed to: chlorine, iodine, nitrogen, and so on. All these diatomic molecules are nonpolar. The bonds are nonpolar. And that's because in each case, the two identical atoms are going to have an equal attraction for the shared electrons, all right? But that's not going to be the case in all cases of bonding, because you're going to have situations where the electrons are not equally shared, especially when the atoms are not identical. Okay, so let's talk about the different possibilities of bonding so far that we have discussed. We talked about ionic bonding, right? And we talked about covalent bonding. And it turns out that ionic bonding and covalent bonding represent two extremes of all the bonding possibilities that one can imagine, all right? Now, if you have two atoms that are not identical, then there will be an unequal sharing of electrons, right? And we call this a polar covalent bond. And what happens as a result is that one atom will assume what we call a partial positive charge, and the other atom will assume a partial negative charge. And therefore, as a result of that charge separation, well, I should say the charge separation result is due to, as we said before, unequal sharing of electrons, because both atoms will have different attraction for the shared electrons, all right? So that's what happens in the case of polar covalent bonding. And I think the next slide is an example of that, and that is the hydrogen chloride molecule. So in the case of hydrogen chloride, as you can see here, the chlorine will have a stronger attraction for the electrons it shares with the hydrogen. So therefore, on average, these electrons that are shared would be closer to the chlorine atom compared to the hydrogen atom. So as a result of that, there would be a distribution of charge that is displaced towards the chlorine, and therefore the chlorine is said to have a partial negative charge, while the hydrogen will have a partial positive charge. So therefore, when you look at the actual molecular orbital that would represent the region in which you'll find the electrons that are shared between the two atoms, the orbital will have a larger lobe around the chlorine atom and a smaller lobe around the hydrogen atom. So that shows you how the electrons are being displaced in favor of the chlorine and away from the hydrogen. So this is just a simple example of what we call a polar covalent bond, all right? So as stated here, the shared electrons will be closer to the chlorine than the hydrogen, and therefore the hydrogen will have a partial positive charge and the chlorine will have a partial negative charge. So these charges are not full charges. So you won't have a plus charge and a minus. We have a partial negative and partial positive. And that's what this sign represents. It's actually a Greek letter, delta, right? So that is used in chemistry to indicate a partial charge. Here, partial negative, here, partial positive. All right. And and this is just saying that the chlorine has a greater attraction for the electron pair compared to the hydrogen. So what that means, therefore, is that the chlorine is more electronegative, right? Now, it says here that the attractive force that an atom, okay, let me see here. What's down here? Okay, so basically they're talking about electronegativity. So basically, the atom with the greater attraction for the shared electrons would be the more electronegative atom, and that's what electronegativity is all about, the attraction that an atom has for shared electrons, all right? Okay, so let me get out of this here and move on to the next slide. Now, this guy, Linus Pauling, he came up with a scale, and if I remember correctly, this was based on thermodynamic data. He developed a scale of relative electronegativities for all the atoms that are represented in the periodic table. So it's a 4-point scale where 4 represents the maximum possible electronegativity value, and it can go from 4 to, well, theoretically to 0, even though there are no atoms with 0 electronegativity. So this is a table which shows you the different elements and their electronegativity values. However, I would prefer that you use another table, which I'm going to show you. It's located in Canvas. So let me go to the Canvas page for this course and show you where you'll find that table. So if you go to Files and then go to Tables and go to Tables Chemistry, and then download that. Okay, come on. Okay, and then, oh, I did that 3 times. Okay, so let me open up Tables Chemistry. Okay, for some reason this is slowing up. Ah, come on. Okay, I don't know what's going on here. For some reason it's, okay, now it's opening up. All right, so the chart or table I'm referring to is located okay, come on, where are you? Right here. Okay, so this is the table that you'll be using for any reference for electronegativity, all right? So this is basically what you'll be using. And as I said before, the maximum number as far as the electronegativity value is 4.0. As you can see, that's fluorine. So fluorine is the most electronegative element. And then you have the others, all right? And a couple of things you'll notice. One you'll notice is that metals tend to have relatively low electronegativity values. So you would have elements like potassium, which is 0.8. I think the highest possible value for a metal is like 1.8, 1.9, maybe 2. And then you'll find that nonmetals tend to have high electronegative values. I pointed out fluorine earlier. Then you have chlorine, which is 3.0, oxygen, which is 3.5, and so on. So that's basically the table that you're going to be using when it comes to electronegativity values. Okay, so we won't be using this table. We'll be using the table that's provided in Canvas. Okay, so some trends that you'll notice with respect to electronegativities. What you'll find is that as you go down any group, the electronegativity will decrease for a representative element. All right, so for example, if you go down group 7A, you'll see that the electronegativity decreases. All right, and that is true pretty much for any representative element or any elements in the representative region of the periodic table. And then as you go from left to right of any period, the electronegativity increases, right? So for example, in period 4, starting with potassium and ending with bromine, you'll see that there's a corresponding increase in the electronegativity values of the elements. So those are the trends as far as electronegativities are concerned when it comes to the elements in the periodic table. It decreases going down any group and increases going across any period. All right. Now, I pointed out this before that when it comes to electronegativities, the metals are typically very low in value, while nonmetals tend to have high electronegativity values. All right. Now, how does this relate to polarity? Well, the polarity of a bond is determined pretty much by the difference in the electronegativities of the atoms that are forming the bond, right? So basically, in order for you to tell whether or not a bond is polar or nonpolar, or better yet, ionic, then you'd have to look at the differences in the electronegativities of the atoms that are involved in the bond, all right? And there's a scale that is used, and in different textbooks, they use different criteria, but the one that we're going to use is the one that's indicated in this chart. So pretty much any two atoms that are bonded to each other, if the difference in their electronegativities lies somewhere between 0 and 0.4, so within this region here, from here to here, these bonds are essentially non-polar covalent, all right? So if the difference in the electronegativities of the two atoms is from 0 to 0.4, then we say that that bond is non-polar covalent. Now, from 0.5 to 1.7, so let me say 0.5, how am I going to do this? Okay, let me put 0.5 here to 1.7 here. Okay, so if you have two atoms bonded to each other and the difference in their electronegativities ranges from 0.5 to 1.7, then we say that the bond is polar covalent. And then finally, if you have a bond of two atoms where the difference in electronegativities is 1.8 or greater, then basically the bond is said to be ionic, all right? And what that means basically is that the charge separation is so great that you have the complete electron transfer from the metal to the nonmetal, and therefore the result would be an ionic bond, all right? So to summarize, I'm just going to construct a little table here. If the difference in electronegativity between two elements is 0.0 to 0.4, then the bond type is non-polar covalent. If the difference goes from 0.5 to 1.7, then the bond type is polar covalent. And then if the difference is 1.8 to higher, then the bond is ionic. So that's a criteria that we're going to use in order to make predictions as to the bond type of a particular bond. Okay, so let me just skip this here. This is just basically summarizing what I just said. So let me get to some examples. So for example, in the case of the hydrogen molecule, they both have the same electronegativity value, 2.1 each. So therefore the difference between them would be 0, right? So therefore this bond would be a nonpolar bond, which comes as no surprise because they're two identical atoms and therefore they will have the same attraction for the shared electrons. So, you know, no surprise there as far as hydrogen is concerned. All right, so the bond is nonpolar covalent. There's another example, two identical atoms bonded to each other, the chlorine molecule. Again, they have the same electronegativity values, so therefore the difference in their electronegativity would be 0, and therefore the bond is considered to be nonpolar covalent. Now let's look at the case of hydrogen chloride. That molecule has, of course, two different atoms connected to connected by a bond, and there are the differences between those two, 3.0 for chlorine, 2.1 for hydrogen. So obviously the difference between them is 0.9, and 0.9 lies within the range I mentioned before, between 0.5 and 1.7. So therefore that would be the polar covalent range. So therefore this bond is considered to be polar covalent. All right. Okay, so, and of course, remember what this means. This means that the electrons are not shared equally between the two atoms, right? The electrons that are shared will be, on average, be closer to the chlorine atom compared to the hydrogen atom, all right? So therefore, you have a charge separation, and the bond is said to be polar covalent. Now, if the bond difference, or I should say, if the electronegativity difference is very large, as in the case of the bond formed between sodium and chlorine, then what you'll see is that you'll have the complete transfer of electrons from the metal to the nonmetal. So in this case, the chlorine atom will have an electronegativity value of 3.0, sodium would be 0.9, the difference between them would be 2.1, and 2.1 lies above 1.8. So therefore, we consider this bond to be ionic. And therefore, basically, there's no sharing of electrons, but the complete transfer of an electron from the sodium to the chlorine, all right? So that's basically how you determine the type of bond that you're dealing with when you have two atoms connected to each other, all right? Another important point being made here in the case of the sodium chloride, and I made this point earlier, but this is just a reminder, that in the case of sodium chloride, there are no molecules of sodium chloride that exist. If you recall, we said that the structure of sodium chloride is basically a crystal structure which consists of an ordered arrangement of the ions, which has basically a repeat unit that continues right throughout the whole structure of the sodium chloride. So there are no molecules of sodium chloride that exist because sodium chloride is an ionic compound. All right, so let's talk about this definition. A dipole is a separation of a charge in a bond or molecule. So that's basically what you'll identify in a polar bond. A polar bond is basically a dipole. And we can simply write a dipole like this, right? Just indicating that one end of the bond or molecule has a partial plus charge and the other end has a partial negative charge. Now, the thing about a dipole is that it's a vector quantity, which means that it has both magnitude and direction. And the directional property of a dipole is very important. You're going to see later on when it comes to molecules. Now, in chemistry, the way we represent a dipole direction is by using an arrow, as you can see here. You have an arrow with a cross at the tail of it, right? So whenever you see this representation here, it's basically showing you the direction of a dipole for a bond. All right, and also for a molecule, which we're going to talk about later on. Now, in terms of the direction of the arrow, it's always pointing to the negative end of the dipole, right? So if you look at a molecule such as HCl, you'll notice that the arrow is pointing away from the hydrogen here towards the chlorine, right? Or in the case of HBr, the hydrogen is pointing away from the hydrogen towards the bromine. And that's because in each of these cases, the chlorine and bromine would be more electronegative than the hydrogen, and therefore will attract the electrons that are shared between the two atoms, and therefore you have that separation of charge, which is a dipole. In the case of the water molecule that is shown here, you'll see that, again, the arrow is pointing away from the oxygen in this case. Away from the hydrogen to the oxygen for both bonds in this case. Again, that's because oxygen is more electronegative than the hydrogen, and therefore you have the electrons that are shared being attracted to the oxygen, and therefore the dipole is shown in this direction here and here in the case of the water molecule. Okay, so let's move on now to talking about a molecule. We talked about the dipole for a bond, but now we're going to relate that to a molecule. And what we're going to look at is a situation where a molecule may or may not be polar. All right, you can have polar bonds and nonpolar bonds, but you can also have polar bonds and nonpolar bonds. Now, as stated here, a molecule containing different kinds of atoms may or may not be polar depending on its shape. So that's a reason why it's important for us to learn about the shapes of molecules. And that will be discussed later on in this chapter. All right. So if we look at the example of carbon dioxide, so this is the structure, the Lewis structure of carbon dioxide. And this is also actually the shape of carbon dioxide. We're going to learn about that later on. But for now, just accept that this is the actual shape. It's a linear molecule where you can literally draw a line from one oxygen through the carbon to the other oxygen at the other end. All right. Now, in this case, the oxygen atoms are more polar than the carbon atom. So therefore, what will happen is that as far as one bond is concerned, let's say this bond, the dipole will be acting in this direction. And then in the case of this bond, the dipole will be acting in this direction, all right? So because the bond, or I should say, because the molecule is linear, these two dipoles will be acting in opposite directions, right? Another important thing you need to recognize is that the magnitude of this dipole would be equal to the magnitude of this dipole. So here we have a situation where we have two dipoles that are equal in magnitude and they're acting in opposite directions. And therefore, what that means, therefore, is that this molecule will have a situation where the dipoles will cancel out each other. And therefore, even though this molecule contains polar bonds, the molecule itself will be nonpolar. And it's nonpolar because the dipoles within the molecule cancel out each other. And therefore, the molecule is nonpolar. All right? So that's basically what happens in the case of a molecule like carbon dioxide, where the dipole moments or the dipoles will cancel out each other, and therefore the net dipole of the molecule would be 0. Okay, so this is basically showing you, oh, we talked about this already. So this is showing you again the different bond types. Covalent, where the difference in the electronegativity would be 0 or almost 0, 0 to 0.4. And then you have the polar covalent, where the difference in the electronegativity would be somewhere between 0.5 and 1.7. And then any difference that is higher than 1.8, or what if it's higher than 1.7, meaning 1.8 or greater, that bond is essentially considered to be ionic. Okay, so now we're going to get into a discussion of the Lewis structures of compounds. Now, if you recall, we talked about the Lewis structures of atoms, and it's a very simple concept. Basically, the Lewis structure of an atom is a symbol surrounded by dots representing the number of valence electrons for the atom. All right, so when it comes to the representative elements, that's very easy to write down for any particular element. Now, of course, when we're talking about compounds, especially molecules, things will be a bit more complicated because, of course, you have different atoms coming together to form a molecule. So now we're going to learn how to draw the Lewis structure of compounds, all right? So first thing I want to mention here is that when you're writing Lewis structures, the most important consideration for forming a stable compound is that the atoms will try to attain a noble gas configuration. In other words, the atom will try to obtain the same number of electrons on its outer shell as its nearest group 8 element, all right? So that's the first thing we need to remember when we're constructing Lewis structures for molecules. Now, I would say that the most difficult part when it comes to writing the Lewis structures is determining the actual arrangement of the atoms in a molecule or an ion. And when we're talking about an ion, we're talking about a polyatomic ion, and we're going to discuss that as well. So for example, when it comes to simple molecules with more than 2 atoms, one atom will be in the center and the other atoms will surround it. So here's an example. Let's say you have this formula here and you're trying to figure out what's the arrangement of these atoms in a molecule. Well, at least on paper, there are 2 possibilities, right? You can have 2 chlorines bonded to each other and then 1 chlorine is bonded to an oxygen, like that. Or you could have 2 chlorines bonded simultaneously to the oxygen in the middle, like that. So the question now becomes which one would be the more likely correct arrangement. And the rule of thumb that we use to make that prediction is right here. Usually, it's either the single atom and or the less electronegative atom that will be the central atom, all right? So in the case of Cl2O, it is more likely that this would be the arrangement where the single atom, which is the oxygen, is simultaneously bonded on either side to two chlorine atoms, all right? In other cases, it would be the less electronegative atom that would be the central atom, all right? But in this case, because you have a single atom bonded to two other atoms, then it is more likely that the oxygen would be in the middle and it will be bonded simultaneously to two chlorine atoms. Okay, so let's talk about the procedures for writing Lewis structures. So we're going to go through stepwise. So the first thing we need to identify is the group numbers for the different elements involved. And the reason why is because the group numbers will give you the number of valence electrons of the different atoms in the formula. So some examples are shown here. So for example, chlorine, which is in group 7A, will have 7 electrons. Nitrogen, which is in group 5A, will have 5 electrons. Carbon is in group 4A, will have 4 electrons, and so on and so forth, all right? So that's the first thing. So you need your periodic table at hand so that you can look up the group numbers, which would give you the number of valence electrons, all right? Okay, so first step in this process is that you obtain the total number of valence electrons to be used in the structure by adding the number of valence electrons in all the atoms in the molecule or ion, all right? Now, if you're going to write the structure of an ion, you need to add 1 electron for each negative charge or subtract 1 electron for each positive charge on the ion. And we're going to look at some examples of that shortly, all right? So basically what you need to do is, based on the formula, you look up the group numbers for the different elements present and you add up all those numbers to get the total number of valence electrons that will be involved in the structure of the molecule or ion. So let's say, for example, you're asked to write down the Lewis structure of water. Then what you'd have to do is go to the periodic table and you look up the group numbers for hydrogen and oxygen. Now, hydrogen has a group number of 1A, so therefore it has 1 electron, and there are 2 of them, so therefore hydrogen will contribute a total of 2 valence electrons, and oxygen is in group 6A, so therefore it will contribute 6 valence electrons. So therefore there'll be a total of 8 electrons, there'll be a total of 8 electrons that will be used in order to formulate the Lewis structure of water. So that's the first step. The second step is that you write a skeletal arrangement of the atoms and connect them with a single covalent bond, right? Now, you can use either 2 dots to represent a bond or 1 dash, because remember, 1 dash or 1 line is the same thing as a pair of electrons, right? So in the case of hydrogen, hydrogen can have only 1 pair of electrons associated with it, right? So therefore it can only form 1 covalent bond. Oxygen, on the other hand, can have up to 8 electrons on its outer shell, or well, up to 8 electrons on its outer shell. Let's leave it at that, all right? So in the case of oxygen, it can have a maximum of 2 covalent bonds, right? Now, the skeletal arrangement will look something like this, all right, where the oxygen is in the middle and the hydrogen will be on either side. Now, it doesn't matter if you're using this arrangement or this arrangement, because for now, we're not concerned about the shape. We're just concerned about how the atoms are connected to each other at this junction, all right? So this would be the skeletal arrangement, or this, it doesn't really matter, all right? And then we start putting the bonding pairs, right? So we can use either 2 dots or a line. So we're going to use 2 dots in this case. So we're going to put 2 dots here and 2 dots here between the hydrogen and oxygen. So we have 2 bonds being formed, 1 bond connecting this oxygen to this hydrogen and another bond right here, all right? Or if you're using this structure here, that would be the arrangement, right? Okay, so basically we have used a total of 4 electrons out of the 8 that would be the total number of valence electrons. So the next question is, where will the other 4 electrons end up, right? So it says here, step 3, subtract 2 electrons for each single bond you use in step 2 from the total number of electrons calculated. So that would be 4 electrons. And then basically that will give you the number of electrons available for completing the rest of the structure. So therefore the other 4 electrons will end up on the oxygen. Let me just jump to this page here. So the other 4 electrons now will end up on the central atom. And now you'll notice that the oxygen has an octet, 2, 4, 6, 8 electrons on its outer shell, while the hydrogens, each of them will have 2 electrons or a duet of electrons on their outer shell. And that would be the full structure of the water molecule, the Lewis structure of the water molecule. All right, so that's basically what's involved in drawing the Lewis structure of any molecule. All right, you have to count out the number of valence electrons, you have to arrange the atoms to get a skeletal framework. You put the bonding pairs first between the atoms that are bonded to each other, and then you put the other pairs of electrons, we call them the non-bonding electrons or lone pairs of electrons on the central atom until each atom has their full complement of outer shell electrons, all right? So that's basically what happens in the case of water. Any questions about this? Any questions? Any questions? Okay, so let's look at this example here. So what I'm going to do is show you how I would normally do it and how I expect you to do it as well. So in this case, we're dealing with carbon dioxide. In fact, let me do this. Okay. Okay, what did I do wrong? Okay, so in the case of carbon dioxide, the first thing I would do is I would determine the total number of valence electrons. So in the case of carbon, that would be 4 electrons. If you go to the periodic table, you'll see that carbon is in group 4A. And then in the case of oxygen, the group number for oxygen is 6A. So therefore, the total number of valence electrons for the as far as the oxygens are concerned, is 6 times 2 because there are 2 oxygen atoms per molecule. So that gives you a total of 12 electrons. And then what I would do is add these up. 4 electrons plus 12 electrons gives you 16 electrons. Now, what I like to do is I like to express them in pairs. So 16 electrons will be equal to 8 pairs, all right? Then what I would do is have the skeletal arrangement of the atoms. And in this case here, because carbon is the least or less electronegative element compared to oxygen, I'd put that in the middle. It's also a single atom. So for those 2 reasons, the carbon will be placed in the middle. And then I would put in the bonding pairs. So remember now, we have 8 pairs of electrons to assign. So the first pair I would put between this carbon and this oxygen. And then the next pair I would put between the same carbon and the other oxygen, all right? So we have used 2 of the 8 pairs, so that means that we have 6 pairs left. So the question now becomes, where will those pairs end up? Now in this case, what we'd have to do is put the pairs of electrons around the oxygens, right, which are bonded to the carbon. So I would put 1 pair here, 1 pair here, 1 pair here, and then 1 pair here, 1 pair here, and 1 pair here, all right? So that's the arrangement as far as the pairs of electrons around the oxygens are concerned. Now, here's one thing that you'll notice, or that you should notice. You'll notice that the oxygen here has its octet. It has 2, 4, 6, 8 electrons, and the same is true for this oxygen here. This oxygen has 2, 4, 6, 8 electrons. But the thing is, the carbon in the middle has only 4 electrons on its outer shell, right? It has 2 electrons here, right? And 2 electrons here. So we need to get the carbon's octet satisfied. And the way that happens is that this oxygen will donate its pair of electrons to form an extra bond right here. And the same thing will happen here. And therefore the resulting structure will be this: C double bond O, and then you have this and this, and then double bond O on the other side, and then you have those pairs as well. And this now would be the final correct answer, because in this case, all the atoms have their octet satisfied. All of them has 8 electrons on their outer shell. So this oxygen here has 2, 4, 6, 8 electrons. Same is true for this oxygen. And as far as the carbon is concerned, it has 2, 4, 6, 8 electrons. And now this would be the final answer right here. So this would be the Lewis structure for carbon dioxide. All right. Okay, any questions about this example? Any questions? Any questions? Okay, so let's see here. I'm just going to jump this here because I went through these steps already. Let me just skip all this here. Okay, let's talk about more complex Lewis structures. Now, there are some molecules or polyatomic ions where, oh, you know something? Before I even do that, let me do a couple more examples because I think I need to do a couple so that you get a good feel for how this is done. All right, so the example I'm going to use is PCl3. Let's try that one, all right? So the first step, if you remember, is that we count up the valence electrons. So we go to the periodic table and we look up the group numbers for these different elements. So in the case of phosphorus, if you look it up, it's in group 5A, so that will contribute 5 electrons. And then chlorine is in group 7A, so that will contribute 7 electrons each, but there are 3 of them. So you have to multiply this by 3. So this gives you a total of 21 electrons, right? So you have 21 electrons here, 5 electrons here. So this gives you a grand total of 26 electrons, which is equal to 13 pairs, all right? Then we arrange the we put together the skeletal arrangement. We put the phosphorus in the middle, surrounded with the chlorines here, here, and here. And then we put the bonding pairs. Now remember, we have 13 pairs of electrons to assign, all right? So the first pair would go here, the second pair would go here, the third pair would go there. So we have assigned 3 pairs so far. Then the 4th pair can go on any one of these chlorines. So I'm going to put the 4th pair here, the 5th pair here, the 6th pair here, 7, 8, 9, 10, 11, 12. So now all the chlorines have 8 electrons on their outer shell. So there's one more pair that is remaining, and that pair will simply go on the central atom here, and that's it. So every atom have their octet satisfied, 8 electrons on their outer shell, including the phosphorus. So therefore, this would be the final answer for the Lewis structure of phosphorus trichloride. All right, so that's how that is done. All right, any questions about this one? Any questions? Okay, so now that I've done 2, I'm going to give you guys the opportunity to tell me what to do for this one. All right. Okay, so what shall we do now? Okay, so suppose you're given SCl2, all right? And you're asked to draw the Lewis structure. So what would be the first step in this process? What would be the first step, folks? Count the valence electrons. So sulfur would contribute how many? 6. And chlorine will contribute how many? 14, because 7 times 2, right? Which would be 14 electrons, all right? So that gives you a grand total of 20 electrons, which would be equal to 10 pairs, all right? Okay, what's the next step? Well, Okay, draw the skeletal structure with the sulfur in the middle, okay, and the chlorines on either side. I would agree with that. And then what? Okay, so put a bonding pair here and a bonding pair here. Okay, very good. So we have used 2 of the 10 pairs. Then what? Well, a double bond. Okay, now that's curious. Why would you suggest that? Okay, yeah, you have to be careful about the total. Remember, we have 10 pairs of electrons and we have used 2 of them to form the bonds here and here, right? So we have 8 pairs remaining. Okay, so you're saying add a pair to each side of all the elements? Well, you have to be careful about that because you have to place the pairs on the atoms in a particular order. You have to start off with the atoms on the outside first, right? So basically, I would put the 3rd pair here, the 4th here, and the 5th here for that chlorine. And then, hold on, wait a minute, what am I doing wrong? 1, 2, 3, 4, 5, then 6, 7, 8, all right? So basically, 6 pairs would be placed on collectively the 2 chlorine atoms, all right? And then we have 2 pairs remaining. Wait a minute, hold on, 1 minute. What am I doing wrong? 1, 2, 3, 4, 5, 6, 7, 8. Right, we have 2 pairs remaining. So 1 pair would go here. Well, the 2 pairs will go on the sulfur atom. All right. So basically, this would be the final answer for the Lewis structure of sulfur dichloride. All right. Okay. So, of course, you'll get the opportunity to do more of these in the assignments I'm going to post or publish online. But basically, you have to practice doing these because the better you become better at it, the more you practice drawing structures. Let's just do one more before we move on to discussing shapes. Okay, so let's say you're given NBr3, all right? So what will be the first step? Well, what's the first step? Okay, so how many valence electrons will nitrogen contribute? Okay, and how many electrons will bromine contribute? Right, 7 times 3, which is 21 electrons, all right? So we add these two together to get 26 electrons, which is equal to 13 pairs, all right? So we put the nitrogen in the middle, surrounded with the bromine, because the nitrogen is the single atom in this formula. And then we put the bonding pairs, 1, 2, 3. So we have used 3 of the 13 pairs. And then 4, 5, 6, 7, 8, 9, 10, 11, 12, and then 13. All right. And as you can see, each atom has their octet satisfied. So this would be the final answer for this. And as you can see, this is, oh, let me take that back. I was about to say this is similar to the previous one, but it's not. So let's leave it at that. All right, so that's basically how we determine the Lewis structures for different molecules. All right, so let's get back to the PowerPoint here. And let's talk about more complex structures where no single one Lewis structure can adequately represent the particular molecule or polyatomic ion. Okay, what's going on here? It's not responding. Okay, so let's say you're given this structure to draw, right? So in the case, in fact, let me do this. Let me do this in this. Okay, so nitrate, NO3 minus. So we go through the same steps as we did before. Nitrogen will contribute 5, oxygen will each contribute 6 times 3, that gives you 18. Now you'll notice there's a negative charge here, right? So what we have to do for the negative charge is add an extra electron, right? So therefore the total number of electrons would be 5 plus 18, 23, plus 1, 24, which would be equal to 12 pairs, all right? Then we put the nitrogen in the middle, surrounded with the oxygens, and then we put the bonding pairs, 1, 2, 3, and then we put the non-bonding pairs on the oxygens, 4, 5, 6, 7, 8, 9, 10, 11, 12, all right? And then you'll notice that the nitrogen does not have 8 electrons on its outer shell, right? So what you can do is you can bring either this pair of electrons here to form a bond, in which case you're going to end up with O, double bond N, O with 3 lone pairs, and then this O with 3 lone pairs. And then what we do is put everything within square parentheses, and we put the negative sign outside because we have a negative charge for the entire polyatomic ion. Now, here's the thing about this particular ion that you have to take into account. You have to realize that this is not the only possible structure for the nitrate ion, because what you can have happening is that this pair of electrons can come down here, and that would push this pair of electrons here, and therefore you can create a new structure which looks like this. Single bond N, and then you have a double bond O, and then lone pairs here and here, and then you're going to have these lone pairs here, right? So the nitrate ion can be represented by, let me bring this up here. The nitrate ion can be represented by this, and it can be represented by this, and there's yet a third structure that can be used to represent a nitrate ion if you push this pair of electrons here and push this pair of electrons up here, and then you're going to end up with N, hope I can fit this down here, O, double bond O, single bond O, and then you put that in square parentheses as well with a minus sign outside. All right, so basically there are three possible structures that can be used to represent the nitrate ion, all right? And in chemistry, we call these three structures resonance structures. Let me go back to the PowerPoint here. Right, so these are the three structures I just showed you, right? And we call this situation here where a molecule or ion can show two or more Lewis structures that are correct and equivalent. We say that the structure exhibits resonance, and each Lewis structure is called a resonance structure. So there are some situations where that can happen, and that typically happens where you have double bonds or triple bonds present in a Lewis structure. All right. Okay. Let's talk about compounds containing polyatomic ions. So a polyatomic ion, of course, as the name suggests, is a collection of atoms held together by covalent bonds, and that unit carries a charge, and it can be a negative charge or a positive charge, but most of them are negatively charged ions, all right? And sometimes they behave as a single unit in chemical reactions. So if we look at, for example, sodium nitrate, which consists of one sodium ion and one nitrate ion, right? Then, of course, the sodium ion, we can easily recognize that as Na+, and the nitrate ion is NO3-. Now, of course, this would be a more complex structure, and therefore, this would be the Lewis structure. We just derived it earlier. This would be the Lewis structure for the nitrate ion, and this would be the Lewis structure for the sodium ion, all right? So that's basically what the polyatomic ion, nitrate ion looks like. Now, as stated here, the nitrate ion consists of one nitrogen atom and 3 oxygen atoms, and they're held together by covalent bonds, and that unit carries a negative charge, which is shown right here, right? So the total number of valence electrons here would be 23, and the reason why that's the case is because nitrogen will contribute 5, each oxygen will contribute 6, so that's 5 plus 18, that's 23 electrons, all right? So that's one nitrogen and 3 oxygen atoms, but you have to add an electron here to make sure that you have a negative charge on that structure. So the negative charge on the nitrate basically adds one additional valence electron. So the actual total number of valence electrons would be 24 in the case of the nitrate ion. And that extra electron actually comes from the sodium, because remember, the sodium has a plus charge. So therefore that contributes an electron towards the nitrogen, towards the ion here, the polyatomic ion. And therefore that's why you end up with 24 electrons for the nitrate, because the extra electron comes from the sodium. Now, it's an ionic compound, sodium nitrate, that is. But you have to recognize that the nitrate part has some covalent bonding, right? So, and that's the result of sharing of electrons between the nitrogen and the oxygen atoms, all right? So basically there are two types of bonds that are existing in this compound. You have the ionic bond that exists between the sodium and the nitrate ion, and then you have the covalent bonds that exist within the nitrate ion between the nitrogen atoms and the oxygen atoms, right? So the ionic bond is between the sodium and the nitrate ion, and then the covalent bond is what exists between the nitrogen and the oxygen atoms that are bonded to it, all right? So what happens when you dissolve sodium nitrate? Well, sodium nitrate breaks down to form separate sodium and nitrate ions. So in other words, there's a breaking of the ionic bond between the sodium and the nitrate ions. So basically, they will separate from each other and be floating around in an aqueous solution separately. You're going to have the sodium ions floating around, and you have the nitrate ions floating around, all right? So that's what happens in an aqueous solution. The nitrate ion will not break up itself. It will still be held together by covalent bonds, and therefore will exist as a unit in an aqueous solution. Okay, the final thing we're going to talk about here, and I hope I can complete this in the time that we have left. We're going to talk about now the molecular shape. So far, we have learned how to draw the Lewis structure of a molecule or ion based on the formula. Based on the Lewis structure, you should now be able to, after completing this section, determine what the shape of the molecule is. So when we're talking about the shape of the molecule, we're talking about the three-dimensional arrangement of the atoms within the structure. And that is very important for us to understand certain properties that the particular substance will display. So believe it or not, based on the molecular shape, you can tell something about, for example, whether or not the compound will have a high boiling point or melting point, or the type of reactions that it will undergo, and so on and so forth. So these are just some examples of molecules and their shapes. And you'll notice, for example, that the water molecule here has what is called a V-shape arrangement. In some textbooks, they call it the bend shape. In the case of carbon dioxide, it has a linear shape. There's a straight line from one atom, from one oxygen atom to the other oxygen atom with the carbon in the middle. In the case of boron trifluoride, the shape is trigonal planar, where you have the boron in the middle, and then you have the fluorine atoms, which are basically occupying the corners of a triangle. And then finally, we have methane, which exhibits what we call a tetrahedral shape, which you can see here, all right? So there are other shapes that exist, but at this level, we're just concerned with these arrangements here and some derivatives of these. We're going to see how that looks shortly. Okay, now the model that is used to explain the shapes of molecules is called the valence shell electron pair repulsion model or theory, all right, or Vsepr, all right? So this is the theory that we're going to use to predict the shapes of molecules based on the Lewis structures. And basically, this model is based on the idea that electron pairs around the central atom will repel each other electrically, and therefore they will spread in order to minimize these repulsive forces. And therefore, as a result of their spreading, the resulting arrangements of these electron pairs will result in a molecule which has a particular shape around the central atom. All right. So as stated here, to accomplish this minimization, the electron pairs will be spread and arranged as far apart from each other as possible around a central atom. So for example, if you look at the beryllium chloride molecule, right? This is the Lewis structure here. And you have two pairs of electrons bonding the beryllium to the other two chlorine atoms. And there are no other pairs of electrons on the beryllium atom. So this pair of electrons will repel this pair of electrons, and therefore they will spread out to be as far from each other as possible. And therefore, the most stable arrangement that will be adopted would be where these electron pairs will be 180 degrees apart, all right? And therefore, as a result, the beryllium chloride molecule is going to be linear in shape, all right? So let me go back up here. So therefore, the shape of this molecule, let me write this down here, is linear, all right? A straight line from the chlorine through the beryllium to the other chlorine atom, all right? So that's what happens in the case of beryllium chloride and pretty much any other molecule where you have a central atom bonded to two other atoms and there are no lone pairs on the central atom. Another example of this would be carbon dioxide. In the case of carbon dioxide, excuse me, you have carbon doubly bonded to two oxygen atoms on either side. Again, this would be a linear shape, and it doesn't matter if the bonds here are double or single or triple. Basically, this pair of electrons or these bonds here, these pairs of electrons will repel those pairs. So therefore, again, the bond angle here would be 180 degrees, and therefore the carbon dioxide, like the beryllium chloride molecule, is going to be linear. Okay, so that's what happens in that particular situation. Now, in the case of a molecule like boron trifluoride, what you'll find is that this is the Lewis structure here. And what you'll find is that the most stable arrangement is where the bond angles here would be 120 degrees, right around, all right? So you have three pairs of electrons here. They're repelling each other so as to be as far apart from each other as possible. And therefore, that's the best arrangement. So the shape of this molecule is said to be, okay, where is the, okay, what's going on here? Oh, okay, is trigonal planar, all right? So that's the shape of the beryllium trifluoride molecule, which is basically the shape of any molecule that has this sort of arrangement, all right? Okay, so that's in the case of boron trifluoride. So as stated here, the bond angles here are 120 degrees, all right? And as I said before, the shape is trigonal planar. Okay, now in the case of a molecule such as methane, where you have the carbon atom bonded to 4 other atoms, the shape that would be adopted is tetrahedral. But before we get to that, let me just say something. It was believed at one point, if you look at the history of chemistry, it was believed at one point that the shape of this molecule is a square planar shape where the bonds are exactly 90 degrees. We now know that not to be the case, all right? And there's a long story behind that, which I won't get into, all right? We now know that the most stable arrangement is actually a tetrahedral arrangement, which you see here, all right? And you'll notice that this results in a bond angle, which is greater compared to what we had before here in the square planar arrangement. In the square planar arrangement, the bond angle is 90 degrees between any 2 bonds. That is now known not to be true. The bond angle is now known to be 109.5, which is gives more room for the bonds to spread, basically. So this would be the arrangement of any molecule where you have a central atom, and that atom is bonded to 4 other atoms, and there are no lone pairs on the central atom. All right. So that is true for methane and true for other molecules that have that arrangement. So this is basically showing you the 3-dimensional structure of methane. One can consider the tetrahedral arrangement as like a triangular-based pyramid. And that's the best way I can kind of describe it. So this is the ball and stick model for methane. And then here is a related compound, carbon tetrachloride. The only difference between methane and carbon tetrachloride is that the hydrogens are replaced by chlorine, but that does not change the shape. The shape is still the tetrahedral arrangement, all right? Okay, so those are the arrangements in the case that would give rise to the shapes I just described, the tetrahedral, the trigonal planar, and the linear arrangement. Now, I want us to look at this molecule, ammonia. If you look at ammonia, you'll notice that the Lewis structure of ammonia is such that the nitrogen is bonded to 3 atoms, and there's a lone pair of electrons on the nitrogen atom, all right? Now, the arrangement of the electron pairs in this case would be tetrahedral because you have 4 pairs of electrons on the central atom. So as far as the electron pair arrangement is concerned, it's basically the same as in the case of methane that we just saw, all right? However, the shapes of the molecules are determined by the spatial arrangements of the atoms, all right? Which is related to the electron pair arrangement. So this is showing you the electron pair arrangement, all right? This is how the electron pairs will be arranged around the nitrogen atom. Now, in the case of ammonia, what you're going to have is that the nitrogen will be bonded to 3 hydrogen atoms, as you can see here, and there's going to be 1 lone pair of electrons or non-bonded pair of electrons on the nitrogen atom. Now, the shape of the molecule, as I said before, is determined by the atoms. So therefore, in this case here, the shape is determined by the nitrogen atom here and the 3 hydrogen atoms, right? So we call this shape a pyramidal shape based on the 3-dimensional arrangements of the atoms, right? It's a pyramidal shape, right? And that's basically the arrangement of any molecule where you have a central atom bonded to 3 other atoms, and there's a lone pair on that central atom. The shape will be a pyramidal shape, all right? So that's what happens in the case of ammonia. Now, in the case of water, right? What you'll see is you have a central atom, oxygen, which has 4 pairs of electrons. So again, in terms of the electron pair arrangement, the arrangement would be tetrahedral, all right? However, again, as I said before, the shape is determined by the actual location spatially, 3-dimensionally of the atoms. So therefore, this is the arrangement of the electron pairs around the central atom. And then the actual structure of the water molecule is shown here, where the oxygen is bonded to 2 hydrogen atoms. And here you have 2 lone pairs of electrons on the central atom. So the shape adopted by the water molecule as a result of this arrangement will be what we call the bend shape, or in some textbooks, they call it the V shape, right? So basically the V would be, or the bend shape would be like this, from the hydrogen to the oxygen to the other hydrogen, and you're going to have these two lone pairs on the central atom, all right? So basically what we have just covered are all the possible shapes for this level anyway, all right? Now, let me get out of this and show you another chart which you're going to use to make predictions of shapes. So let me go to here, get out of this, and okay, so you'll notice here you have this particular document, the Vsepr theory document. So let me download that. And this is what you're going to use. Okay, why is it not opening up? Okay, so this is what you're going to use to make predictions about shapes of molecules, all right? Now, for our level, introductory chemistry level, you'll only be using up to the third line. So here, here, and here, all right? You won't be using the last two here. That's for general chemistry 1, all right? So basically, let me explain what's happening here. In each case, the E represents the central atom, and the X represents the atoms that are bonded to the central atom, all right? So for example, if you have a central atom bonded to two other atoms, right? Then the shape adopted here would be linear, all right? If you have the central atom bonded to 3 other atoms, then the shape adopted by the structure would be trigonal planar. If you have a central atom bonded to 2 atoms and also has a lone pair of electrons on it, then the shape would be bent or angular, all right? And you have similar descriptions for the others as well. So this is what you're going to use to make predictions as to the shape of a particular molecule. So for example, if you, can I write on this? Let me see, draw, okay. Okay, let me use, this. Okay, so for example, I think one of the examples we used was SCl2. And if you remember, the Lewis structure for SCl2 is S bonded to Cl, bonded to Cl, and you have 2 lone pairs here, right? Well, this structure here would correspond to this arrangement right here, right? You have the central atom, which is the S, bonded to 2 other atoms, which would be the chlorines. And that central atom also has 2 lone pairs, which would be this lone pair and this lone pair. So therefore, we can predict that the shape of this molecule will be bent or angular, all right? Or V-shaped, all right? So that's basically how you're going to use this chart. So this chart is what you're going to refer to if you're given any question that deals with molecular shapes, all right? So I just thought I should point that out to you. Okay, so just to summarize, going back to the PowerPoint, when it comes to determining the structure of a molecule using Vsepr theory, first you have to draw the Lewis structure. We know how to do that from before. Then we look at the electron pairs around the central atom, and we try to arrange them in order to minimize repulsions, and then determine the positions of the atoms based on that. And then you're going to name the molecular structure. So you're going to say whether or not it's linear or bent or trigonal planar or trigonal or pyramidal or whatever. All right. So that's basically how you determine the shapes of molecule. Okay. So that represents the end of chapter 12. So that means, going back to the Canvas page, as far as assignments go, you should be able to do, let me see here, assignment 34, 35, and 36. So let me make sure that those are published. Okay, so it is published, right? So those assignments must be completed by, well, By next week. I'll give you until next week this time. But before you leave, let me just say something. So according to the syllabus, your test number 2 should be next week, but I've decided to put it off until the following week. And in terms of the topics that will be covered by that test, let me check my records here. So what I've decided is that test number 2 will basically cover chapters 5 through 8. Let me just check something here. Right, 5 through 8. So chapters 5 through 8. Now the corresponding assignments would be assignments 8 through 17. Let me make a note of that. All right. So I'm going to require that you guys, if you have not done so yet, make sure that you have submitted all assignments completed up to assignment 17 by Friday, because what I want to do is grade them and then send them back to you so that you have it to review. And I'm also going to post the answer keys next week, all right? So that you'll have it to review in preparation for your test the following week, all right? So I just thought I should let you guys know that. Okay, I see a question in the chat. How do you know? Oh, I'm sorry, Taryn, I didn't realize that you asked a question. You said, how do you know which atom will be in the middle if all the atoms of the element are standalone atoms, such as in the case of NaOCl? Well, in that case, I would say, let me see, NaOCl. Which one is, well, the most electronegative element I would place in the middle. So that would be oxygen. I would place that in the middle, and then I was surrounded with a nitrogen. But if I'm not mistaken, hold on, let me see. You know what? Let me check that out and get back to you on that one. It would be the least electronegative element that would be in the middle. So in this case, that would be chlorine, if I'm not mistaken. Of course, I'd have to look at the tables to see, but I think it's chlorine. Oh, it is the first question on assignment 35. Yeah, I don't think it matters if it's either chlorine or nitrogen. It depends on which one is less electronegative. So you have to consult the table. All right. Okay. So I'm going to post in the announcements what I just told you guys, right? About the test, about the assignments that are due this Friday, and I think that's it. And what the test will be based on, chapters 5 through 8, for which the corresponding assignments would be assignments 8 through 17. All right. So that's basically it. If you have any questions, feel free to contact me during my office hours because I can't field any more questions now because time's up. All right. So I'll see you guys on Wednesday. All right. And then on Wednesday, we're going to move on to chapter, what is it now? 14. All right. Okay. So that's it for today. Take care. And I'll see you guys on Wednesday. Oh, I'm sorry. Monday. We're meeting on Monday. My brain is fried. I'm sorry, folks. We're meeting on Monday. All right. I'll see you guys on